Okay. Related rates are really just an application of implicit differentiation over and over again. They're all really like just different application problems. So they're all different.
Yeah.
And so it's like, yeah, we did a lot of examples, but it was just really the same general process or like thought process of implicit differentiation over and over again. The hardest part is
relating the rates.
Yeah. Because then the math is easy because you just implicit differentiate.
Yeah.
There were a couple more examples that I was hoping we would get through, but we ran out of time last week, and that's okay. We have to keep moving forward, but I have a plan for how we're going to figure it out. There's a problem that we're in the middle of, the baseball problem, number whatever, 20 something.
Yeah.
And so you're going to do part B of that. There's also one that I want us to do where we're trying to solve for the rate of change of which the angle is changing. We've done a lot of sides, we've done a lot of like shapes.
There was one of those.
There was one, I think, in the videos, I think there was one.
Yeah, maybe.
And then maybe in math. But regardless, I want us to actually do one.
Right.
And then there was an old AP one that I wanted to go through as well. But because we ran out of time last week, which is fine, and because we need to keep moving forward, I gotta make up a day somehow. So what I'm gonna do is tonight I'm gonna record a video of me teaching through those problems, and I'll post that. And then that's part of your tomorrow assignment, is to just watch that video, copy down the notes and problems. And then that's pretty much. There will be other things that post tomorrow, but you don't have to do tomorrow, other than one thing. But I'll talk about that again at the end of class, but that's my plan. Since we need to keep moving forward, and I need to make up a day, I'm gonna make you watch a day at home. Okay. Okay, I feel better. Okay, here we go. Yes, because I just had chicken and I could feel it in my teeth. Not gonna do that. Okay, way back at the beginning of the year, we studied limits. And we mainly studied limits so that we could define the derivative, right? The formal derivative definition has a limit built into it. But there's one idea that we played around with briefly, but not for a long time, definitely didn't formalize it. And we purposely did not spend time on it. And that idea is limits that involve infinity. So we're going to revisit that topic today. So limits at infinity and infinite limits are different. But also completely similar. So they're completely distinct and completely similar. We have to know the distinction, but there's definitely a relationship. That's what we're going to be talking about today for the next 10 minutes, so it's going to be fine. It's really easy. The difference is super easy. A limit at infinity means that as x increases without bound towards infinity, then the f of x function is going to approach some number L. I did not leave myself space to write that, but a limit at infinity is when limit as x increases without bound, then f of x is going to approach some number L. An infinite limit is when x approaches some number a, whatever that number might be, then f of x is going to blow up to infinity, or f of x is going to grow without bound. That's the main distinction. I'm going to revisit this notation again in a couple of minutes, but I just want to show you these examples so that we can get our intuition on it, and then we'll work with it. So here are some examples of limits at infinity versus infinite limits. What do you notice? What do you notice? Nothing's too obvious.
Between the first limit at infinity and the first infinite limit, the values just flip.
Okay, you mean this value and this value?
Yes.
Okay. Yep, so 0's here, infinity's here, and then they flip-flop there, okay? Great. What else do you notice?
Just for the first one.
Sure.
Is the bottom right supposed to be 1/x squared, or is it supposed to be 1/x?
1/x.
Okay.
Yep. Yeah, starting with these first four is easiest to talk about first, but why do you think I wrote in green and pink?
I think you could make a distinction between infinity and other values.
Okay. So these all the green is infinity. Okay. Good. That's the first thing we have to see. What do you notice about where the infinities are at? There's only two of you. I can't get it wrong.
You got it,
You
John.
got it.
I don't know. I'm just trying to figure out why the x is not squared for them.
I just picked functions. I just picked functions. So
Three just happened to be the same.
I picked functions on purpose because I'm trying to illustrate other things, but it's just a function. Yeah. Okay. What do you notice about where the infinities are at?
Like approaching versus the is equal to?
Yeah. Which one has the x is approaching infinity? In other words, x grows without bound.
When it's equal to 0.
At infinity.
Yeah, when the limit's at infinity. In this case, they do both equal 0. Maybe that's always true. I'll have to think about that. Okay. So maybe every time x grows without bound, it equals 0. We'll have to think about that. But the limits at infinity have the infinity inside the limit notation. The infinite limits has infinity as like the answer. Okay. So this connects right back here. Limit at infinity is this one. This is an infinite limit. Could you describe the difference between them, just from what you know so far? What do you think?
For the first one, any x, you put in along like just a number chain, as no matter how far that grows, the limit is always going to be the same for that x value, as long as it keeps going. And then, well, not at like, maybe I should clarify, not at like x equals 1 or like x equals 2, but if you have an x value that's like so big it's practically infinity, then the value is always going to be the same for that L. And then for the limit approaching any sort of value, I don't know how to like explain that per se, but I mean it makes sense in my head. I just don't know how to tell it to you.
Sure.
In
What do you got?
the limit at infinity, the x value is approaching infinity, and then in infinite limit, the y value would be approaching infinity
Yeah, that's a good way to put it.
at a certain x, or
Mhm.
a, I suppose.
Yeah, as x approaches whatever number you want, 5.
Can't you have them in both terms?
Well, oh, infinity here and infinity here.
Yeah.
Maybe. I'll think about that too. Okay. Okay, good. So this idea is really intuitive when you look at graphs. Okay, so this is going to help you trying to get a handle on what's happening here. So let's graph these first 4 and see what's happening, and if we can connect the math notation to the graphs. Let's see, maybe I can do. Okay, apparently that doesn't work.
Is it possible to do a limit function on this?
Just graph the actual.
Oh,
In short, yes, but also no. Okay, the first one we've got is 1 over x squared. Okay, can I make this smaller? Yes, I can. Please make it smaller. No, I can't. Alright. Fine, then we won't. Alright, what do we see here about x squared? What's its behavior? 1 over x squared, I should say, not x squared.
There's an asymptote at 0.
Okay, there's an asymptote at 0. Interesting. Why?
Because if you put 0 in, it would be undefined.
Okay, 0 is undefined. Why doesn't it go below 0?
Because it's squared. And so any negative number would become positive when it's squared.
Wait. Yep. Okay. So range goes from 0 up, excluding 0.
Mm-hmm.
Okay. What else do you notice? Let's talk about this first one then. Limit as x is approaching infinity, or limit as x grows or increases without bound of this function is equal to 0. Can we make sense of this by looking at the graph?
Mm-hmm.
Tell me. Jonah, tell me.
well, for either direction, if you go to negative infinity, since it's squared, it's never going to be a negative value, and so it's just approaching that y equals 0 point the entire way. And then it's same for the right side. And then once it approaches 0 for an x value, it's straight up because there's an asymptote. And so whatever value you put in, it's just, as long as it's approaching infinity, it's just going to be 0 all the way. Maybe not for the middle though. Like if I had like x equals 2, probably not, as long as it's growing.
Yeah, x equals 2. It's so close. What'll it be?
0.5-ish.
0.25.
Yeah. Yeah, the scale here, there's the 2. Yeah.
Oh wait.
So then that makes it a little clearer to see. But yeah, if you plug in 2 here, you get 1/4. So, a quarter. Okay. So yeah, 2, probably not getting close to 0 really yet. A quarter is very different from 0. But pick any arbitrarily large value of x, you're pretty small. And you're just gonna keep getting smaller. Okay. Same thing if you go the other way. Pick an arbitrarily small number for x, negative number, you'll get something really small. Okay, then you added something else. You said something about an asymptote in the middle. Okay. Where's that at?
0. Well, you can have 0 in the denominator, so.
Okay. So if I can't put 0 in the denominator, could I use limits to see what would happen if I got really close to 0?
Yeah.
Sure. What if I came from the right side? My x values came from the right side towards 0. What's happening?
Your y value grows exponentially.
Yeah. Exponentially. It's really really linearly. Well, quadratic.
Sort of.
I don't know how to say that, but it's not
grows very
exponentially.
fast.
It grows very fast. It blows up.
Yeah.
Big.
Okay, it's going very fast. So those y values are growing without bound.
Yes.
Okay. All right. So they're just going to keep getting bigger and bigger. What if you come from the left? If you come from your x values from the left, what's going to happen?
Keep going.
Yeah, it's going to also go all the way up to infinity. Okay, so this is the notation to show that, right here. The limit as x is approaching 0, this is from both sides, but the limit as x approaches 0 from both sides of this function is infinity. Oh yeah, duh, that makes sense. It'll look like it's infinity, right? This is much easier to look at with a graph and go, oh yeah, obviously as I keep going east on the x-axis, it's gonna be, I'm gonna be getting to 0, right? Okay, great, so that helps us explain these parts. As x grows without bound, as x decreases without bound, you're gonna get to 0. As x approaches 0, then you're gonna go find infinity. Okay, that is the difference between an infinite limit and a limit at infinity. A limit at infinity says, I'm traveling to infinity and I want to see what's there. An infinite limit says, I'm hanging out at home, I'm at 1, I'm at 0, I'm at 5, but I'm sky high. That make sense? Okay. 1 over x going to negative infinity as x approaches 0 from the left. Okay. Let's graph that. See what it looks like. 1 over x. Okay, there's 1 over x. All right, let's talk about its behavior.
It's very similar to the last, except the left side of the y-axis is reflected over the x-axis.
Yeah, there's definitely a lot of similarities. Yep. So what happens as I approach 0 from the left? Graphically.
Asymptote.
Yeah, I'm going to be approaching this asymptote at 0, right? They keep coming closer and closer to 0 from the left. All of a sudden I go all the way down here really fast. If I was at 0.0000001, I'm going to be way down there. So this is why we say the limit as x approaches 0 from the left of this function is negative infinity. Because it's going to blow down all the way. Okay? What happens as what happens as x approaches 0 from the right? Positive infinity.
Mm-hmm.
What happens as x approaches infinity?
0.
0. What happens as x approaches negative infinity?
0.
0. Right. Then we can talk about what happens when the limit as x approaches 10.
Would be whatever value it is at 10.
It would just be whatever the value is at 10. We could plug 10 in. Right here, sorry.
So 1/10.
It would be 1/10. That would be the limit as x approaches 10. It would be 1/10. We wouldn't even really have to do much for that.
Mm-hmm.
But since I can't ever actually make it to infinity, I have to think about, okay, what would happen if I could make it to infinity? What would I see? Or, because I can't actually plug 0 in, because that's undefined, what would happen if I got really arbitrarily close? Then I would basically know what's happening at 0.
Mm-hmm.
Right? This is just going back to limits. This is really not a lot of new things, but this is like, we gotta get our hands on this. Okay, let's go back to some of these other ones. Okay, I have a few more on here. Let's just start with these ones. Sine x does not exist as x approaches infinity. Explain it.
Because sine is oscillating, there's no specific value it approaches as it approaches infinity.
Yes.
Versus like the other ones tend towards a certain value.
Mm-hmm. Right. Sine is constantly oscillating, so we never really know what's going to happen at infinity, except that it's just going to keep changing. So that does not exist. Okay. As x approaches infinity of x squared, apparently that's infinity. Why?
Well, I mean, infinity times infinity is just more infinity.
Sure.
Kind of a nonsensical thing, because
Yeah.
zero times
Yeah, what's
zero is
infinity
just-
times infinity? To infinity? Right. Why would it be infinity but not like a number?
We don't really specify.
Yeah, but like here we had, as x is approaching infinity or negative infinity, that's a number. You got 0. I mean, if I shifted the graph, that could be 1, right? It could just be a number. How come this is actually, apparently f of x is approaching infinity as x approaches infinity? Why?
Like the nature of a parabola is that it goes x increases to infinity and y also increases to infinity. So then the limit of x squared as x approaches infinity would also be infinity because that's where y is 10 or more.
Yeah, does this function tend towards a specific value as you keep going bigger as x increases with that bound? No. That number is just going to end up getting even bigger than whatever your x value picked. So this, we just say it goes off to infinity.
Mm-hmm.
So can you have 2 infinities?
Not really.
Yeah. No, your other question. Not infinity times infinity. Yes, you can't do infinity times infinity. Can you have an infinity here and an infinity here? Yeah, you can. There's a great example. How about this one? Does e to the x approach a certain value as it gets bigger?
It's not trending toward anything, because it's just a constant value, and then to an exponent, so I guess, yeah, if it was negative, it'd be 0.
I don't know, it kind of looks like it's trending, right? Doesn't it kind of look like it's tending towards something? Doesn't seem like it's going past 100 very soon.
Yeah.
Could it ever go past 100?
Yes.
Keep scrolling, I guess.
Keep scrolling and find out.
Yeah, it's scrolling for a while.
Doesn't even look like it's making it past 25.
I think I saw it move.
What do you think? Could you find an x value for which e to the x is going to be 100? What if you say 100 equals e to the x? How'd you solve for x?
Natural both sides. That would be x equals natural. Or
E equals natural log of 100.
yeah, it would be x equals natural. I believe. Because natural log of e is just 1.
If you take the natural log of y equals e to the x, you would get natural log of y times x natural log of e.
Yeah, and we said y was 100.
Yep, and y is 100, and what's natural log of e?
1.
1, so the natural log of 100 would equal x,
Yes.
2.
which is 2.
Yeah.
X equals 2.
Should be.
Natural log, I don't actually know, I'm really bad at it. Natural log of 100 is not 2.
It's 4.6.
Oh, whoops, I had just log.
Oh, yeah, that would definitely be different.
Hmm.
Okay.
Yeah, 4.6.
Oh, let me zoom out. That's smart. Look at me be smart. Okay. Okay, so it will eventually hit 100.
Yeah.
When x is like 4.6. Weird, right? But could you put in an x value of like 40 into e to the x?
Yeah.
Sure. What's stopping us? Could we put in an x value of 1,000,000?
Yeah.
Yeah. There's really nothing off of the domain list here.
Right.
So this is why e to the x, even though it doesn't go very far very fast,
Still.
actually does go off to infinity.
Yeah.
That's weird. But if you put in a sufficiently high enough x value, you can get a sufficiently large e to the x value. Okay? All right. Let's talk about, let's see, we talked about those. Let's talk about this one. Is this an example of an infinite limit? Because remember, these ones had 0 here, and they went off to infinity. This one has 0 here, and then it equals 1. This is not a good example of an infinite limit, because what happens if you plug in 0?
2 e x. This is 1.
1 equals 1. Oh, I can actually just find that limit.
Yeah.
Right?
Yeah.
This is not an example of an infinite limit. This symbol means not in math. Okay, so let's talk about, yeah. Let's find this limit. It was on page 231. We gotta keep pacing here now. We'll be fine. Just as long as by then I start that. Okay, graphing this would make it really easy to guess the value of the limit. Actually, so let's actually just start there real quick. Oh, is it gonna let me, it's not gonna let me do it halfway again. Okay, as long as I can see it. X squared plus 1. Oh, I should have put all that in parentheses. Divided by 2x squared plus 3. Okay. So here it is. So graphing it would make it really easy for us to find the limit of this. As x approaches infinity, what are we trending towards?
1/2.
Yeah.
Yeah.
It's hard to see, but
I
there's
but
1 and there's a half.
Yeah.
As you keep going, we're just gonna keep getting a half. So there she goes, just at a half the whole time. We've already found the limit. We know it's gonna be half. Graphing makes it really easy. But algebra can also powerfully clinch the case here. So here's how we could algebraically find this limit without needing to use graphing. We've done this at the beginning of the year. Showed you guys a couple of examples like this. But we're gonna take this limit, and what we're gonna do is we're gonna factor out the largest x term. The largest x term on the top is x squared. Let's factor that out. Can you factor out x squared from 1? Fun fact, you can. You can factor out anything you want ever. You just have to make sure that it's true when you distribute. So if I take out the x squared, I'm going to leave 1 behind for the first term.
1 over x.
But if I have 1 over x squared,
Okay.
I can factor out an x squared where there are no x's. Okay? If I distribute this, do you agree that I get back to where I had?
Yes.
Great, then we're good. Okay, the largest x term on the bottom is also x squared. So we're going to factor out the x squared. X squared is 2 plus 3 over x squared. That x squared. Okay, there you go. Okay, so we're factoring. The reason we do this is because I can cancel these from the top and the bottom and leave me with a form of this limit of which I can actually take that limit. What happens if I try to put infinity in here right now? Let's talk about that. If I put infinity right here, a million squared plus 1 is a hecton. 2 times a million squared plus 3 is even more than that. But a half, we know that it's going to be a half. How do we know it's a half? Right? So this is really hard to see as it is.
Yeah.
When you put in infinity, what's going to happen? Okay? You could put in some big X values into your calculator and probably get something close to it and be like, oh, okay, maybe I see a pattern. That's tedious. So this strategy is going to help us be able to take the limit at infinity by factoring out that largest term. Okay, so the x squareds there cancel, and that will leave us with the limit as x approaches infinity of 1 plus 1 over x squared. Johnny, you're going to want to copy this down.
Sure.
Okay. Turn in your textbook to page 207. Okay, and then quickly get caught up on it. The theorem on page 207, theorem 5, tells us things that we can do with limits. It says, hey, if you have the sum of 2 things, but you're taking a limit, you could take the limit of each of those individual things.
That's
If
not
you...
207, but
It's not 207? Oh, 207. Okay, isn't 23?
2.
Maybe it's 107. Yeah, I just wrote it down wrong. Definitely 107.
Yeah.
Okay, I'll change that in my notes. There you go.
Yes.
Yes, so 107. Okay, there we go. That's fixed. All right, so if you have a limit and you've got some stuff on the inside of that limit, you could take the limit of each of these terms that are summed together. That's also true with multiplication and division. That's all there in theorem 5. So would you agree that I could take the limit as x approaches infinity of 1 plus limit as x approaches infinity of 1 over x squared all over the limit x approaches infinity of 2 plus the limit x approaches infinity 3 over x squared. Do you agree? Good with that? Okay. What's the limit as x approaches infinity of the function 1?
1.
Yep. What's the limit as x approaches infinity of this function? What happens if you put in really big values into that denominator? What's going to happen to that function?
Closer to 0.
It's going to get real close to 0. Okay, so that limit's going to equal 0. So the limit as x approaches infinity of 2. And how about this last one?
0.
0. What? That 3's not going to cancel it out?
Probably not.
No, that's not going to do nothing. Okay, so there we have a very simplified version now of this limit. What does this simplify to?
2.5.
Bingo.
Yay.
Which we already knew, so that was a great verification. So algebra will let us like powerfully calculate these really tricky limits where it's like, oh, I don't really know what to do, and I'm not allowed to graph because I'm on the AP exam and whatever. Then there you go. Okay? Okay. All right, I know this is really groundbreaking for us, but this is all good. Okay, so remember I said that infinite limits and limits at infinity are different but related?
Mhm.
Okay, so they're similar because they both involve the infinity symbol, but they also both involve asymptotes, which we kind of already saw a little bit. But they're different in the fact that they relate to horizontal and vertical asymptotes respectively. Which of these two in red relates to or represents horizontal asymptotes, and which one represents vertical asymptotes?
Isn't the right one a vertical?
Okay, how come?
Because the y value is directly horizontal.
Because the y value is growing with that bound or decreasing with that bound. And it doesn't matter if you come at A from the right or the left, it doesn't matter. If you end up going to positive or negative infinity, that's a vertical asymptote, right? Okay, so process of elimination, that's a horizontal asymptote, right? Whether you go off to positive infinity or negative infinity,
Mhm.
if you're approaching some value, like maybe a half, then that's a horizontal asymptote. Okay? Great. Let's use the same logical process that we did for that problem in orange right here for you to solve these limits. I'm going to give you let's see. Just do the first and the second one for the sake of time, and then go as fast as you can. And then I'll actually, you do the first one, you do the second one.
Okay.
I'll do the third one.
Okay.
Go. All right, see if you can finish up in 10 seconds. Alright, can you see the end, Elsie, or?
Yeah,
Okay, what do you get?
3 halves.
3 halves, okay. So I'm assuming you pulled out x squared to begin?
Yep.
Okay, so we'll cancel an x squared out of everything. Be 3 plus 2 over x plus 1 over x squared.
Mm.
I should write limit, because I technically have a limit here still, okay. And then that would be 2 plus 1 over x minus 3 over x squared?
Yep.
Okay, great, and that would be 3 halves. Because this term will go to 0, that term will go to 0 when you take the limit. When you take the limit, when you take the limit. So you have 3 plus 0 plus 0, 2 plus 0 minus 0, we 3 halves. So this, the limit of that function, is a nice little 3 halves. I mean,
See.
you got 3 halves?
Yeah.
Okay. So you did 3 plus 1 over x squared. Okay. Over.
X.
Again, I should write limit here. That's bad notation. Okay. Over
X minus 1 over x.
x minus 1 over x. 2 minus 1 over x?
Oh, sorry, yeah, 2 over 1.
Oh, but you still have an x out here.
Right, next, so there you
Yes. Okay.
go. There's,
Okay, so we have this x out here. 2 minus 1 over x. Okay, what do we make of this x then?
what's it?
The top would have an x squared outside of it still.
Oh, the top should have the x?
Yeah, the top,
Top
should
should
have
have,
X.
yeah, top should have an x.
Okay, yep, good job.
And the bottom would cancel.
So there's x here. Alright, what do we make of this x? Can I plug the limit in yet? Or do we know what's going to happen? Why don't we pause and we'll look at mine. I have a single term x on the top and a double x squared x here. I actually took out x squared out of both of them, even though I only had the one x there. Is that legal?
Yeah.
Yeah. There you go, there you go, there you go. If I cancel those, put the limit in here, it'll be 0, limit here is 0, limit here is 3, limit here is 0. 0 over 3 is 0. Can we think like that for yours? Could we maybe pull out x squared here too? That way we don't have this x? Let's try it. If I pull out another x from the bottom, then that x would cancel. And I'd have this. We're quick with that? Okay, all right. What's the limit of each of those terms?
0.
3 plus 0,
This is just
0 minus 0.
Does not exist.
Yes and no. Can you divide by 0?
No.
No, right out. But remember that we factored out that extra x to help us just see what's going on. And we're not actually dividing by 0. We're taking a limit, right? But let's think about it then in terms of if I had this x here still, and I had an x multiplied by that stuff over this stuff going to 0, which of those two is going to be more dominant? If this one's going off to infinity and this one's going to 2 minus 0, what happens if you divide infinity by 2? Infinity. Okay. That was not my best question, but are we good with that?
Yeah.
Okay, because this one is actually infinity. Okay. We're gonna see another way to do this on Wednesday that's even better, but holy smokes, we are out of time, which is super sad. Yeah, we have 30 seconds. Okay. Oh, that's bad. We need to go further. All right. Let's go as far as we can. I might just go a minute past the bell. I'm going to summarize all of this so that we can move on Wednesday. We've got, let's use red. I'm gonna call this asymptotes of limits. They're not really asymptotes, but I think it's a helpful way to think about it. Asymptotes of limits. I'm going to summarize this with math notation. So those three examples are examples of this. If I have the limit as x approaches infinity of some coefficient k1 times x to some exponent y1. And that's all divided by some number k times x to the y2. I'm indexing these numbers because I want you to see that there's a connection between the variables. Like there's a connection between the exponents, but they're different numbers, or they could be different numbers, okay? In this case, the y1 is going to equal the y2, and in that case, you're going to have k1 over k2. That will be the value of the limit if those degrees are the same. Let's look at this first example. Your highest degrees are the same, so we got 3 halves. There's your 3 and there's your 2.
Yes.
Okay, cool. So there's the math language for something really intuitive. X approaches infinity of, there's 3 cases here. There's the case where the exponents equal each other. There's the case where the denominator's power is smaller than the numerator's power. If the denominator's power is smaller than the numerator's power, then the numerator takes over and grows faster than the denominator, so it's going to be infinity. That's a case of Jonas. This power is greater than this one. It takes over, so it's going to be infinity. Okay, one more case. Shocker, you could probably guess. K1, x to the y1, where y1 is going to be smaller than y2. X to the y2. What is that going to equal? Yes, 0. My example was the example of that. This power was greater than this one, so we went off to 0 because the denominator took over. It was bigger. Okay, so there's the fancy math language for it. And we successfully made it only halfway through what we needed to do that. Tomorrow, I'm going to send you a video that you need to watch. I'm going to try to keep it under an hour. It should only be like 30 minutes, I bet. But I'll send you that, watch that, copy the notes down into your related rates section notes, and then we're done with related rates. So I'll post those notes after I make that video. I'll send it to you tonight. Tomorrow you are also, my phone is recording, so I actually can look. I'm going to post homework 12, but it's not due until next Monday. I'm going to post things on AP Classroom, also not due until next Monday. So you don't even have to do that tomorrow. You'll watch the video that I send you, and then I want you to read 4.2, pages 220 to 227, so not the whole chapter. Read and watch a video is all you have to do. Okay. All right, good job today. Isn't that what you gave me?